So, welcome back to this week. Last week, we concluded the lecture session with the disadvantages of the Raman spectroscopy. So, that is why I put the slide in front of you. So, we talked about that Raman spectrometer, which consists of lens and capturing part of the scattered radiation and directing it to a filter to let only the Raman scattered light to be sensed by the detector. So, we have realized that Raman shift, unfortunately interference and instability issues prevent Raman spectroscopy from providing accurate glucose measurement in vivo. So, due to this reason, though Raman spectroscopy is a very powerful tool for in vivo glucose detection, possibly, but it is not currently exploitable at the commercial zone because of too much noise in the signal. In the same line, the last week I told you that we will talk about far infrared spectroscopy. One thing to be realized when we talk about the far infrared, we are trying to detect the weak bonds, weak vibrational rotational motion, which are prevalent in the biological systems. But you really needed a very unique signature when you are trying to do that from outside, means in vivo. When you are taking the pure sample and putting it in a spectrophotometer, it is a different story. But when you are trying to read these or get these readouts directly from a subject, a human or an animal or any other moving system or living system, there are a lot of interferences. And as we talk about far infrared spectroscopy, which is also called as terahertz spectroscopy, is based on the principle of absorption due to existence of particular vibrational and rotational transition of weak bonds and bonds of heavy atoms, approximately between, this is the number you have to realize, 0.3 terahertz, which is 1000 micrometer, to 30 terahertz, which is 10 micrometer. The lack of information on FIR or far infrared means that the technology is still in its infancy concerning the field of non-invasive glucose detection, as I was mentioning. Since the strong absorption of water and the low level of power delivered by terahertz sources do not allow detection of meaningful data using standard NIR MIR methods. Nevertheless, with the advent of quantum cascade lasers, OCLs or quantum cascade lasers, now it is possible to use time resolved far infrared spectroscopy, also called terahertz time domain spectroscopy, for biomedical application in the sub-millimeter wavelength range. So, this is the part which is of significance of the use of quantum cascade lasers, QCLs, just to correct it. So, this is QCLs. It is possible to get a time resolve far infrared spectroscopy, and this particular development in laser technology has opened up a lot of opportunity for using far infrared spectroscopy for in near future for in vivo glucose estimation, but not with the traditional far infrared spectroscopy, but using QCL techniques. Next area where there is a lot of work which is going on is time of flight or TOF, which is the mass spec, and terahertz time domain spectroscopy, which we talk about THZ and TDS. Okay, TDS stand for time domain spectroscopy and THZ stands for terahertz. Okay, and that is the short form. And time of flight, they call it a TOF. So, we need TOF uses a single frequency, very short laser pulses in order of picoseconds to measure the radiation absorption and time it takes photons to travel across the sample. So, you are using the laser pulses in the order of picoseconds to measure the radiation absorption and the time it takes photons to travel across the sample. It uses the same spectroscopic principle of absorption and scattering, but from a time domain perspective to get the phase change as an additional parameter. So, this is the part which is of significance, the phase change. When light propagates through the sample, some photons will follow a direct path towards the detector, while others, so some will follow like this, while others will follow a longer zigzag path due to multiple internal reflection to the detector. Detector stands here for D, and others will go through the total scattering, giving rise to diffuse light, something like this. Analyzing the time of flight distribution of detected photons, the change in the pulse shape and pulse broadening due to scattering and absorption level, it is possible to detect the optical properties of the medium, including glucose concentration. But when I am making these drawings, you must have realized that when we are talking about doing such analysis in vivo, there are a lot of noises and interference. If we could bring these down, then definitely one can get a very unique signature. Alrazo et al., this is the author, described a typical setup for measuring glucose in vitro. Again, see, they are using it in vitro with TOF using 35 picosecond pulses with a wavelength of 905 nanometer, hitting a sample and an array of 5 optical fibers, collecting the scattered light from the medium and directing them towards camera to record a temporal profile of the detected pulses. Besides Alrazo's measurement, TOF needs further study for glucose monitoring. So, when we are talking about say for example, here you have a sample in a cuvette, a pure glucose sample or a blood sample, or urine sample or any other, or a sweat sample. So, these are the samples where the laser light could have a direct accessibility. They are in a laser, so you have a direct accessibility. But when we are talking about on a skin, you are trying to do this. In the body, there are a lot of layers. You have the skin, epidermal layer, subepidermal layer, before it reaches to the blood vessels. So, during that process, there is a lot of interference and noises which are generated, and this is the major problem whenever we are talking about time of flight, time domain spectroscopy at terahertz level. All these techniques suffers from these interferences. So, most of the spectroscopic technique, while they are some of the finest signatures, yet when you translate them from in vivo to in vitro, the equation changes. So, if there is a way that in vitro data could be corroborated with the in vivo data, same signature, then these techniques will find place in day-to-day in vivo measurements of glucose. Okay. Now, next we move to another form of a spectroscopy, which is called thermal emission spectroscopy. So, we all are aware of the fact that due to the metabolic activities in our body generates heat or heat radiation. So, while our body generates a heat signature, it is a cumulative of all the reactions taking place. But assume from that heat signature or the radiation, if we could detect the level of glucose. See, in other words, the generation of heat is the cumulative of multiple metabolic processes with the body, but from there, say for example, it is contributed by 10 parameters. If you could pick up the glucose parameter, then you will be able to do so. So, we are talking about thermal emission spectroscopy, which in short they call it TESS. uses the principle that human body naturally emits energy as heat in the far infrared bands, okay, between 8 micrometer and 14 micrometer. So, as a matter of fact, animals detect human using exactly that kind of far infrared sensing. As a matter of fact, snakes use these kind of technologies. They could sense. Okay. During the process of leaving the body, part of this radiation is absorbed by different molecules in the body, including glucose, around 94.4 micrometer wavelength. So, while body is generating them, okay, there is this glucose which is absorbing it before it goes out. Now, meaning that analysis of the intensity and characteristic of such radiation, figure will follow, provides useful information on the presence of the concentration level of glucose in the tissue with reasonable specificity. So, in other words, say for example, here you have a cuvette where you have the glucose molecule sitting in some kind of a solution. Okay. Now, here is the far infrared bands. Now, when they are passing through, say for example, so some of it is getting absorbed by these molecules, and what is going out is after the absorption. So, now depending on how many particles are there, if number of particles increases, then automatically there will be more absorption, and that is what it meant by provides useful information on the presence of concentration level. Now, this is one of the profound possibility, thermal emission spectroscopy, and here is the picture. So, for example, these are the heat generated by the body, this is the body tissue. Now, there are a lot of glucose present, depending on the concentration of the glucose, what they are absorbing. So, this is the original, say for example, radiation amount. Because of the absorption, there is a lesser one here, and here is a thermal sensor. If it compare depending on the glucose level of the body, so you back calculate it by using another technique, that say for example, from this tissue you draw the blood and measure the glucose by another in vivo or in vitro technique. Now, similarly, you feed the animal with sugar and then you draw the blood and measure the glucose. So, now you have without sugar you have glucose measurement, with sugar you have glucose measurement, and the thermal sensor will have two different kind of absorption which will come through, and that absorption will give you the amount of glucose versus the sensitivity or what the thermal sensor is telling you. And this is the basis of thermal sensing using thermal emission spectroscopy. So, this is another profound technique. So, these kind of technologies needs a lot of testing with the in vivo, in vitro, and here it is a in vivo measurements. This in vivo and in vitro measurements, when you quantify them together, what you get is the deviation from the in vitro to in vivo data. Now, that deviation is nothing but, say for example, your in vitro says X amount of glucose and your in vivo says Y amount of glucose. That means from, and assume that Y is less than X. That means that amount which is less is X plus delta X will be equal to Y. Since delta X is the amount which is getting lost because of interference and other losses due to the presence of other absorbing molecules which are of similar nature. So, unless these two values, that in vivo is correlated with in vitro value, and the error level is being determined, these sensors will need a lot of work before they get commercialized. It is almost like, think of a thermometer which is measuring temperature. It's a mercury thermometer. That mercury thermometer has gone through many decades of perfection, when now we know that okay, this much rise indicate this much change in temperature. Exactly like a mercury thermometer, here we have to figure out with how much increase in glucose, how the radiation changes. Second part of this thing is that this tissue is whose, depending on what is the physiological status. First of all, a gender, is it a male or a female? Then comes, there are races who have better, they generate more heat, their metabolism is higher. So, say for example, is the subject a Caucasian, or is a subject is an Asian, or a subject is from people with a darker skin code, or they are coming from places which are extremely cold, or they are coming from places which are extremely hot, or they are coming from places which are at a very high altitude, or they are doing some special kind of exercise like underwater exercise or other things, or in the submarine. Depending on your physiological status, the heat generation is altered in the body. Especially those who work on sports medicine, they all realize it. So, unless we have tons of in vivo data corroborated with the in vitro data, it is very tough to get an exact picture. In theory, these are fantastic techniques, but in terms of practical applications, they suffer from series of challenges which have to be overcome in the decades to come. So, however, just reading and interpreting the radiation absorbed by glucose is not enough to provide accurate reading due to small amount of thermal energy involved, and this is another part. Thus, TES also compares the reading with a predicted amount of thermal energy using Planck's distribution function, in which the measured data is the intensity reference level upon which the actual thermal absorption is calculated and then converted to glucose concentration level. So, you see the complexity, and that whole picture will make more sense to you when we talk about the Planck's distribution, and from the Planck's distribution you are measuring the intensity of the small amount of radiation what you are getting. Unfortunately, although in theory, as I was mentioning you, this technology seems to be straightforward, it's pretty straightforward. No significant research has been put into it. As such, there are several limitations that needs to be addressed. The most acknowledged experiment using TES is the one performed by Bouchard back in 2004 in the tympanic membrane, but actual in vivo results need yet to be published. So, this is something worth looking, that though in theory this is one of the most beautiful technique, but when it comes to the practical applications, it suffers from series of drawbacks, and unless these drawbacks are met, unless these challenges are being rectified and corrected, these technologies will not be able to make the cut for commercialization. Same as what we discussed about time of flight and terahertz domain spectroscopy. Same is true for far infrared spectroscopy. So, while most of these technologies are of immense importance, they are extremely challenging. Yet, there are places where these technologies could be utilized in a very different context. When we talk about situations like where you have soldiers who are put in desert warfare system, or in a high altitude system, or there are sports situation where you have to go through some special training, There these kind of data is amazing, because you exactly know the condition in which you are putting the individual or the human, or in case human subject. There you can get the extreme of the extreme data. So one of the things in management of these kind of sensors, assuming in 20 years these will become the technology or technological breakthrough, one needs to generate data from extreme environments, because these are really potential tools to get generation of data from, say, hyperbaric hypoxic situation, where there is a low pressure and low oxygen, body has to really fight it out, or you are in a submarine, or you are going for a deep sea diving, or you are going for a scuba diving, or you are in space, or you are going for, say, a desert warfare system. So much of these things, and second part is that these data needs to be verified across the different uh, races, different ethnicities, because these have potential, but this needs a very broad level of data collection before we have a clear picture of how these data could be utilized or could make sense in the longer run of commercializing these technologies, especially while we are talking about sensor integrated suits for warfare system, biowarfare systems. These are some of the tools. See, standalone, none of these will make sense, but when you integrate them with multiple technologies, they all will make sense. Okay, say for example, you have a suit. In that suit, you have all these things integrated. You have a thermal sensor sensing it, and there is a software which is embedded into it, which is doing all the Planck's distribution and deducting from the Planck's distribution, possibly glucose level, and you have a sensor which is the other sort of sensors which are present in the whole system. So you realize that much of this sensor business will use a lot of printed electrodes, which we'll be talking very soon, probably next week or this week. Lot of miniaturization, lot of bodily integration, where much of the sensor technology will capitalize for in vivo recording. So we'll close in, and the next class we'll talk a little bit more about the rest of the technologies for in vivo glucose sensing. Thank you.